this is very greedy, but sometimes you can get it. So, and now we're talking about toric varieties, which is what I'm going to be looking at the most. So for me, toric variety is an irreducible closed variety of complex dimension n with the action, and I'm going to always standardize by torus. So this is an n-dimensional complex torus, but I would like it to be c cross to the n, which acts on X with a dense orbit. And just to point out, a lot of other speakers allowed affine toric varieties. That's great, but just for simplicity, I'm just going to say toric variety and stick with the closed case. So what are some examples? Well, the first example I really want to focus on are Herzbergs surfaces. So you take P1 and you take a line bundle over it with Chern class minus M. So a holomorphic line bundle with Chern class minus M. And we'll just call that O of minus M. That's the sort of the standard notation. So that's a line bundle over P1. And then we add to it a trivial line bundle. So now we have a C2 bundle over P1. And then we projectivize it, and we get, what we get is a P1 bundle over P1. So these are famous classical toric varieties, and the torus structure is easy to see. So we can act on P1, obviously, by spinning it as a natural C-cross action. We can lift that action to the line bundle O of negative M, and then that gives us an action on the vector space when we sum with C, and then it gives us an action on the projectivization. So that's one of the actions. And the other action is you just spin the two line bundles in each fiber. So just a fiber-wise spinning. So that gives us a 2 torus action. Great. And another important example is bot manifolds, sometimes called bot towers, but anyway, I'm calling them bot manifolds. So this is very similar. We start with P1, and then we're going to define it inductively. And generally the way you do it inductively is once you've defined xn minus 1, you pick some equivariant holomorphic line bundle L over it. You add a copy of the trivial line bundle, and you projectivize. And that will be the n-dimensional step. And it's going to be a P1 bundle over xn minus 1. So for instance, your first step is P1, your second step will be a Herzberg surface, and then you keep on going. So the simplest example would be a product of P1s, but in general, it can be twisted. Any questions so far? Okay, great, I'll continue. So we've already talked about this, but smooth toric varieties, so I'll be looking at the smooth case, are easy to classify up to equivariant diffeomorphism, or really equivariant biholomorphism. So we've already seen that. We've talked about fans. That's appeared in a number of the talks, and those are giving a very good equivariant classification. But it's much harder to classify them up to diffeomorphism, because you're sort of leaving the category. So for example, we have a very nice theorem due to Masuda. So let X and X prime be smooth algebraic varieties. So if there's an isomorphism of the equivariant cohomology rings that takes the equivariant Chern class of X to the equivariant Chern class of X prime, then X and X prime are equivariantly diffeomorphic. And this is essentially sort of the equivariant analog of rigidity, except that we need the Chern classes, which is actually necessary. But that's due to Masuda. So that's the equivariant, where the story is fairly nice. And then we have a question, which was first posed by Masuda and Su, which is, are smooth toric varieties cohomologically rigid? So in a sense, this is quite a bold conjecture in my mind, because like I say, cohomologically rigid is just a very nice property, which generally fails. Right? So let's talk about some results. So the first theorem I want to talk about is a theorem of Masuda and Penov. So suppose that X is a bot manifold, and the cohomology ring of X with integer coefficients is isomorphic to the cohomology ring of a product of P1s. Then the conclusion is that X is actually diffeomorphic to a product of P1s. Another theorem by Choi and Masuda a little bit later was saying that if you have two Bott manifolds and both of them have trivial rational homology, so it's called often Q trivial homology, but you see that I'm assuming that the cohomology of X over the rationals is isomorphic to the cohomology ring of a product of P1s for both of the manifolds. So then I say, okay, great. Now, if I know that their integer cohomology of these two manifolds is also isomorphic, then the two manifolds are diffeomorphic. So in terms of our previous terminology, we're saying that the family of Bott manifolds with trivial rational cohomology is cohomologically rigid. So great, so this is another special case. In fact, there are a number of other special cases where this theorem has been known. Different theorems with a number of authors combined. Cho, Choi, Lee, Masuda, Panna, Park, and Su are some of the names. And many of these focused on either more general things about Bott manifolds or generalized Bott manifolds. Generalized Bott manifolds are similar to Bott manifolds, but instead of having everything be P1, we allow different projective spaces. So it's a more general case. But the important thing to point out is there's no known counterexamples. So as far as we know, this theorem, the question is still open. The original question is still open. We don't know whether or not all smooth toric varieties are cohomologically rigid. Okay, so that was pretty much everything that I had to say about just plain old cohomologically rigidity. Is there any questions or comments? Okay, great. So I guess I'll go on to the next part, which is I want to talk about symplectic cohomological rigidity. Okay, why is this not working? Ah, there we go. Sorry. Okay, so now we want to talk about symplectic cohomological rigidity. So now, instead of just looking at a family of manifolds, as you might expect, we're going to look at a family of symplectic manifolds. So let's fix M omega and M prime omega prime in a family. So we're going to fix two elements of a family. So now it's obviously not going to be enough. So now we have an even stronger statement about the invariance. So if M and M prime are symplectomorphic, then there's an isomorphism from the cohomology of M to the cohomology of M prime. And obviously, since this is a symplectomorphism, it has to take the cohomology class of omega to the cohomology class of omega prime. So now the question is, suppose that we have an isomorphism, so the converse. Again, we're going to ask for the converse. So suppose there's an isomorphism from the cohomology of M to the cohomology of M prime, and that isomorphism takes the class of omega to the class of omega prime. Does this imply that M is symplectomorphic to M prime? And if the answer is yes, then we're going to say that the family is symplectically cohomologically rigid. Right, and so we obviously need to include the assumption on the cohomology class. Otherwise, this will obviously be false, right? Because the two sphere can have different areas. And so those are obviously the cohomology rings the same, but not, they're not symplectomorphic. So this is obviously sort of the weakest thing that we could hope for. Hold on one second. sorry. So we again have a very easy example, which is that symplectic surfaces are symplectically cohomologically rigid, because in this case, all you need to classify them is the genus and the area. And obviously those are easily read off of the ring and the class in the ring. Okay. Okay. So what family are we going to look at? So instead of looking at toric varieties, we're going to look at symplectic toric manifolds, which are more or less the same thing, but from a symplectic point of view. So I want to set up my definitions. So by a symplectic toric manifold, I mean I want a 2n dimensional closed connected manifold M. So again, I'm insisting on closed. And I want an integral symplectic form. So I just mean I want the cohomology class of omega to be an integral class. So again, that's not always assumed, but I want to assume that. And then I want to have a faithful S1 to the n action on M. And I'm just going to call the vector field induced by the jth S1. I'm going to call that Cj. And I'm going to have a moment map mu from M to Rn. Of course, this is just a map such that if I take take omega and I apply it to Cj, then I get minus d of mu j for all j. So this is all familiar to, I think, many of you or all of you. But the important fact is by Atiyah, Gilman, and Sternberg, the moment polytope delta, which is just the image of M under the moment map, is a convex polytope. It's actually a convex rational polytope, but we won't need that. So what are some examples? So really, the most important example from our point of view is any smooth projective toric variety. And when I say projective here, I'm actually going to assume that my manifold X is given as a subvariety of Pn. So if you prefer, you can say it has a very ample line bundle, but I'm sticking with thinking of it as projective variety. In particular, and I should say for this one, there's actually a converse that every symplectic toric manifold is a smooth projective toric variety. So you can really look at these things as almost equivalent. And in particular, every Bott manifold. So we saw them at the beginning, and in fact, I claim they are projective toric varieties, so they can be embedded into Pn. And in this case, we're going to call it a symplectic Bott manifold. So this is what we mean by a symplectic Bott manifold. Oh, and I should say why, of course, why is a smooth projective toric variety symplectic? Because there's a symplectic form, the Fubini-Studi form on the projective space, and we restrict this to X, and that gives us a symplectic form on X. And that is what we mean by a symplectic Bott manifold. Any questions? Okay. All right, so I want to talk a little bit about symplectic Bott manifolds. So, great. So let M be a symplectic Bott manifold with moment polytope delta. So the first thing I want to claim is that delta is combinatorially equivalent to a hypercube. So that means that you can have a one-to-one correspondence. So hypercube, I just mean take an interval and take n products of it. And what I mean by combinatorial equivalent is that there's a correspondence of the faces, so that every face of delta corresponds to a face of the hypercube of the same dimension, so that the faces of delta intersect if and only if the faces of the hypercube intersect. So it has a very simple intersection. And moreover, we can write this in a very simple combinatorial way. So there's always going to be a strictly upper triangular integral matrix A, and a vector lambda in Zn, such that the polytope delta is given by the set of all P and Rn, such that if I pair P with Ej, it's greater than or equal to 0. And if I pair P with Ej plus the sum over I, Aij, Ei, it's less than or equal to lambda j for all j. So here we see that the normals are the Ej and the Ej plus the sum over I. well, I guess it's minus EJ, and the sum, and EJ plus the sum over I of AIJEI. But this formula, it's maybe not so important that you get the details. I just want to point out that these A and lambda are exactly describing the polytope. And there's an additional fact, which again has been referred to, but we have a very explicit, and none of this is, I mean, this is just sort of well-known stuff, but there's a very explicit formula for the cohomology ring of a toric variety, of a smooth toric variety in general. We've had some talks about sort of where you can extend that, but in the case, if you apply it in this case, it's very straightforward. And you see, we get a very explicit formula for the cohomology ring and for the class omega. And moreover, this is somehow a very natural presentation because the xj are actually dual to facets. So it's this facet. This facet gives you, so this description gives you a facet of the polytope. If you take its preimage under the moment map, you get a submanifold, and xj is the Poincare dual to it. So again, if you haven't seen this before, it just looks like a formula, that's fine, but just note it's a very explicit formula. That's the main point. Okay, great. So in particular, let's talk about one specific case. What about the Herzberg surfaces? Well, if you look at the formula, we're gonna say, okay, what does this tell us? It's topologically, it's combinatorial equivalent to a square. Okay, so in fact, all that's allowed in this case really is it's gonna be a trapezoid. So great, so the mole polytopes are always trapezoids. And the cohomology ring is just given by two generators, x1 and x2, and it's subject to x2 squared. The kernel is generated by x2 squared and x1 squared plus mx1, x2. So that's pretty simple. And so I want to give two particular examples. We can look at the 0 Herzberg surface, which is just P1 cross P1. So now the moment image is always going to be a rectangle. I've chosen a particular form here, but that's fine. And sigma 2, you can see in this case, you can see the 2 because the 2 is the slope of this side. And generally speaking, that is what the M is going to do, is it's going to tell you the slope of this side. So these are nice integral polytopes for people. Anyway, so these are good examples to keep in mind. The Herzberg surfaces are really sort of the key example here. Okay, great. So just like we said before, symplectic toric manifolds are easy to classify up to equivariant symplectomorphism. So that's really sort of the natural and easy thing to do, but they're much harder to classify up to symplectomorphism. So it's obvious sort of that if M and M prime are equivariantly symplectomorphic, then their moment polytopes are just going to differ by translation. And the theorem due to Delzant is that the converse also holds, that if delta and delta prime differ by a translation, then the toric manifolds are equivariantly symplectic. So great, so the equivariant case is pretty easy. But we really want to talk about the symplectic case. And so now we have the natural generalization or analog, it's not really generalization, of the question that Masuda and Sue asked, which is, are symplectic toric manifolds symplectically cohomologically rigid? Maybe I'll go back a slide, and just from what we know, this is a very reasonable, maybe a reasonable thing to hope. At least we have one nice example. So we know that Herzberg surfaces, so if you look at like a sigma A and sigma B, two different Herzberg surfaces, it's well known that those are diffeomorphic if and only if A equals B. I mean, that's like a really old fact, right? That's sort of the point of Herzberg surfaces, is they're diffeomorphic, but they have different complex structures. So I don't even know when that's due, but it's due to Herzberg. And symplectically, a similar statement has been known for a long time as well. So these two polytopes here, of course, the polytopes look quite different, and there's no way to take any kind of affine translation of one polytope into the other. You know, they're just different polytopes. But in fact, it's been known for, I think it's a folklore theorem, really. I saw it back when I was a grad student, and I don't know who it's originally due to, that these manifolds are symplectomorphic. So you can see that they have the same area, and they have isomorphic cohomology rings. Because if you add a 2 here, you can see that you can find an isomorphism that I think you take x1 to x1 minus x2 that intertwines the two maps. That gives you an isomorphism from one to the other. And if you check, you can see it takes this omega to this omega. So we know that they're symplectomorphic. So if you look at what we know for Herzberg surfaces, it's sort of very easy to check. Like when we first saw this, we're like, okay, great. This sort of clearly is true for Herzberg surfaces from things people already knew. And so it's sort of a natural question to ask, like, okay, great. Does it work for other cases? And in fact, Mcduff proved a generalization that she says, but kind of a fairly special case. So if M is a symplectic toric manifold and the cohomology of M with integer coefficients is isomorphic to the cohomology of the product of two projective spaces, then M is symplectomorphic to the product of two projective spaces. So here, when I just say symplectomorphic to the product, I mean, you can take the Fubini's Studi form on each of them and pull it back to a product symplectic form, possibly with different weights. So sort of the natural symplectic form. And there's been a number of other partial results due to Karshan, Kessler, Pinnicel, and Mcduff. Sorry, I'm losing my voice a little bit. But most of these other results are not actually saying that things are symplectomorphic. What they're saying is that there's a finite number. So this goes back to Liat's talk. So she wasn't looking at the toric case, but when you have a finite number of tori. So that's not quite, if you can only have a finite number of tori, that's sort of some ways towards proving this, but it's not quite it because you won't know that you actually have an isomorphism. Okay, so, oops, sorry. So now I've given the background so I can talk about our main results. So our main results look very much like these two results that I started with, but now they're in the symplectic category. So the main result is, so let M and M prime be symplectic Bott manifolds. And we're going to assume that their rational cohomology ring, again, is isomorphic to the rational cohomology of the product of P1s. So again, trivial rational cohomology. So the claim is if there's an isomorphism from the cohomology of M to the cohomology of M prime that takes the class of omega to the class of omega prime, then M and M prime are symplectomorphic. So in other words, symplectic cohomological rigidity does hold for this class. So particularly if you don't love Bott manifolds, there's a nice corollary which doesn't use that statement. Just if M is a symplectic toric manifold and its cohomology ring is isomorphic to the cohomology ring of P1 to the n, then M is symplectomorphic to P1 to the n, where we have the symplectic form, which I'm calling omega sub lambda, which is going to take the Fubini Studi form, and I'm going to pull it back to pi I is going to be the projection onto the ith copy of P1. If I take that and I pull it back, I multiply it by some real number lambda I, and I sum it up, I'm going to get a symplectic form. So it's sort of a standard product symplectic form, only I'm allowing all the sides to be different. And the corollary is very easy to prove from the main theorem, because there's a result of Masuda and Paniak that says, under this case, M is a symplectic Bott manifold. And then once you know it's a symplectic Bott manifold, it just follows trivially from the main theorem. And there's one note I just wanted to mention, which is that strong rigidity also holds. So there's a stronger version of this statement that says that if you have an isomorph, given a specific isomorphism of cohomology rings that takes a mega to mega prime, there's a symplectic morphism between them that induces that map, induces that isomorphism in cohomology. So that's the strong version, and everything we're saying, we also prove the strong version of, and I think everything I referred to, there is also a strong version. But just for simplicity, I'm sticking with the basic statement. But for experts who might care, that we have that too. Okay, so I know I haven't been getting too many questions, but I think this is a good place to stop, because now I've stated our result, and I'm going to move on to proving it. So does anybody have any questions about what we are proving?
You're not getting any questions because your talk is a model of clarity.
Excellent, excellent. That's always the hope, whereas the fear is like everyone's left and is like, you know, binge drinking with their friends someplace. Okay, okay, great. Oops, that's not what I wanted. Okay, so I want to talk about the proof of the main theorem. So what's really important is there's sort of one important new idea in this paper, which is that we need to construct new symplectomorphisms, right? So there's not, I mean, you can just sort of naively hope the theorem is true without constructing symplectomorphisms, but clearly you just don't have enough to make that work. So you need to find some new ones. And otherwise, the proof is pretty similar to what has already been done by like Panabasada-Su in the smooth case. It's not identical, but it's pretty similar. So I don't think that's the interesting part to repeat. I really want to talk about what's different. And this is where, this is our new proposition, which is suppose that we have two symplectic Bott manifolds. Okay, so suppose you have some k less than L and an isomorphism from the cohomology of M to the cohomology of M prime. So of course you need to take the class of omega to the class of omega prime, but I want to assume this isomorphism has a very special form. I want to say, okay, it has to take xk to xk prime minus gamma xl prime for some gamma in z. And it has to take xi to xi prime for all I not equal to k. So here, what do I mean by the xi? Well, go back to this slide. Oops. Right, these are exactly the xi in this formula. These duals, and the xi primes are hopefully obviously the analogous thing for M prime. So these are our standard generators. So this is a very special kind of isomorphism, but in this particular case, we can prove that M and M prime are symplectomorphic. And then it turns out to be that this is a very special kind of isomorphism. It's sort of the key isomorphism, and everything else we can get just sort of like by hook or by crook pretty straightforwardly, or by applying sort of standard transformations of polytopes. So polytopes that are, you know, we may have to take a polygon, polytope, sorry, and you know, we know that if we have another one, which is an affine linear transformation, they're the same manifold, so we'll have to do that. So from now on, I'm going to focus on proving this proposition, which, like I said, I think is the interesting case. Why do we have a symplectomorphism in this case? Okay, so this is where toric degenerations come in. So if Megumi is here, I'm going to slaughter her paper, but hopefully not in a bad way. So we want to start with a smooth projective variety X. So remember, that means to us it's inside projective space. So I want to fix a local coordinate system on X. So I want to take a coordinate patch on X, which is an identified part of X with Cn. Now, what I'm leaving out is a lot of what Megumi was talking about, which is I'm going to use this, I'm going to get evaluation and blah, blah, blah. I'm not going to focus on that. But great, it's just we need to choose a local coordinate system, then we can apply the process that she described. And as she says, we're going to get an associated semigroup. Oh, shoot, there's a typo. Oh, well, there's a typo. S, and I want to write S as the union over M. Oh, no, this is fine, sorry. As the union over M greater than 0 of M cross SM sitting inside Z cross ZN. So she was talking about it, well, Q, but never mind, is sitting inside Zn plus 1, but the first Z is actually kind of special, and I actually want to sort of just pull out that Z and talk about the different layers. So it's like a cone, sort of, maybe not precisely, but vaguely it's a cone. I just want to talk about each slice. I want to give that a name, SM. And so the Akunkoff body, so this is what she called the Newton-Akunkoff body. So it's defined to be, so I take SM and I divide that by M, and then I get a bunch of points. And then I take the union of those over all M, and then I take the convex hull, and then I take the closure. And this is going to give me something that's called the Akunkoff body. And there's a theorem that we're using due to Urbana-Champagin, which is assume that S is finitely generated. So that's an important technical condition. So then if we take C of S and take its projectivization, we get a toric, a projective toric variety, X naught with moment polytope delta. So I'm cheating a little bit. In general, this is not smooth. Essentially what you like to do is, I think of this as taking your manifold and like squishing bits of it kind of violently. And so generally you'll mess that up. It's not smooth, but it sits inside a projective space, and the torus extends to an action on the projective space. So you can just restrict the moment map from a projective space to X naught. Call that your moment map. Great. So you can still talk about a moment polytope. And the main part of the theorem is there's a continuous surjective map phi from X to X naught, and it's a symplectomorphism on an open dense subset of X. So this is what their theorem tells us. And Jeremy was talking earlier about how this lets us have a torus action on an open dense set, and that's great. And like I said, usually X naught kind of comes up kind of smushed and deformed. But if X naught is smooth, it's sort of a miracle. It generally doesn't happen. But if you look at their theorem, it's clear that if X naught is smooth, then this map phi is actually a symplectomorphism. And this is going to be the important thing. This is where we're getting symplectomorphisms. And Megumi did, well, I want to talk just a teeny bit about the idea of the proof of their theorem, which is you construct a toric degeneration of X. So this is just a flat family. So it's a variety curly X and map pi from C. And the generic fiber of this map is going to be isomorphic to X, and the fiber over 0 is going to be X naught. And then what they do is they could take a radial vector field on C, and they lift it to this curly X, and that gives you the flow. With them, you integrate the flow. So anyway, it's a very brief sketch of the proof, but that's how the idea works.
Excuse me, Susan.
Yeah.
What did you mean by generic fiber is isomorphic to X?
Right. So this family X is one dimension. I'm sorry. The family curly X is one dimensional bigger than X. So if you look at like pi inverse of 1, you're going to get a variety which is the same dimension as X, and it actually is isomorphic to X. Does that make sense? You take any value other than 0 and take the preimage, like if you take any value A not equal to 0, if you take pi inverse of A, this will be a variety. And the claim is that I want that variety to be isomorphic to X as a variety.
Algebraically isomorphic.
Yes, algebraically isomorphic. And with the line bundle as well. Preserve the line bundle as well. So it's pretty strong. I mean, it's a pretty strong condition. Did that answer your question?
Thanks.
I mean, I know I did not give adequate details of their proof. This is not meant to be a complete. There's lots of things to check here, right? I mean, they wrote a whole paper on it, but that's the idea. The idea is actually quite simple, which I like. Okay. So, so to get into more of the details, so that's sort of the big picture of this theorem, which is quite general. I want to talk about something we call the slide operator. So you fix a W in Zn, and I don't want all the coordinates to be non-negative. I want at least one negative coordinate. So here we have in my picture is minus E1 plus E2 is my W. So right, so I've drawn arrows. So they might want to take some subset Q of the positive orthant. And I want to, I can slide that set along W. And the way I do it is I slide each point as far as possible within the positive octant or orthant in the direction W. So here's a very simple example. So I can only slide along these red lines. And you see, if I look at this bottom one, oh, there's no place to slide it. Here, no place to slide it. Here, no place to slide it. But if I look here, you see, aha, I can move this dot one point this way, and I get this dot. This is just, do you see how I got from the left picture to the right picture by sliding my dots? Okay, great. And then I just want to point out, if I take the convex hull of these dots, in the one case, I'm getting the rectangle, and in the next case, I'm getting a trapezoid. And you may recognize these pictures, right? These are the same pictures that I got a number of slides ago that were just the moment polytopes of P1 cross P1 and the Herzbergs 2 surface. Okay, great. So that's the slide operator. Any questions about the slide operator? Because it's kind of the key. Okay, so now we're almost done. Once you know what a slide is, so now in order to prove the key proposition, which was just that I have a symplectic morphism in this special case, I need to prove two sub-propositions. And the first is, so let's say I have symplectic Bott manifolds, M and M prime, with moment polytopes, delta and delta prime. So I want to assume there exists K less than L and an isomorphism from the cohomology of M to the cohomology of M prime that takes the class of omega to the class of omega prime. So I always need that, but also has this very special form that I talked about before. It needs to send xk to xk prime minus gamma xl prime for some gamma in z. And it needs to send xi to xi prime for all I not equal to k. So again, this is exactly the form I had before. So now I have the slightly annoying technical condition. Remember, these were associated to these upper triangular matrices A, these strictly upper triangular matrices A. So if the KL coordinate of the A prime matrix, the matrix for M prime, is bigger or equal than the absolute value of ALK, so it's just sort of an annoying technical condition, then there exists, then there exists C greater than or equal to 0, so that I can get the so I can multiply by any M. So I can take looking at M delta and M delta prime, just means that I can expand my polytope as much as I want, is that I can get from the polytope delta, well, the integral points in the polytope delta to the integral points in the polytope delta prime just by sliding. So, so again, this is exactly what I had here, where I say, great, I can get from this one to this one just by sliding. And I'm saying that that's a perfectly general statement. Whenever I have them related to each other by one of these special isomorphisms. And then this slightly annoying technical condition is not too hard to get rid of, because either sometimes you have to slide from M to M prime, and sometimes you have to slide from M prime to M, and then sometimes you have to sort of flip them over and then slide, but that part's all pretty straightforward. So in that case, I can slide from the one polytope to the other polytope, and that's one half of the proof. And then the other half of the proof is just for any symplectic toric manifolds with moment polytopes delta and delta prime. But I want these polytopes to be equal to the positive orthant near 0. So again, I can always achieve that. I just have to put them into standard position. So you see here are my coordinate axes. You see, if I just look at a little neighborhood of 0, both of these polytopes just look like the positive quadrant. So that's good. So I want to assume I've put my polytopes into that standard form. And then if there exists K less than L and C greater than or equal to 0, such that if I take delta and its integral points or multiples and slide them along this vector, then I get the other polytope. If one polytope is the slide of another polytope, then the two manifolds are symplectomorphic. And the way we prove this proposition is by finding an explicit coordinate chart that actually, well, the way we prove this the way we prove the second proposition is saying, hey, we can prove that x naught then is going to be this, x naught is going to be m prime in this case, and we can prove explicitly that it's smooth. So, well, yeah, I mean, I guess it's smooth. We proved that M prime is the polytope we get at the center. Okay, so I think that's it. So I'm done.